All right, Chapter 4, Section 1, describing the relation between two variables. Okay, so in this section, we're going to cover scattergrams and correlation. We're going to draw and interpret scattergrams. We're going to describe the properties of linear correlation coefficient. We're going to compute and interpret the linear correlation coefficient. We're going to determine whether linear relations exist between two variables, and explain the difference between correlation and causation, right? Two important different things. Okay, so a little bit of definitions first. The response variable is the variable whose value can be explained by the value of the explanatory or the predictor variable, right? Often we just refer to it as the explanatory variable more than the predictor variable. A scattergram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in a data set is represented by points in the scattergram. The explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. Okay, so here's an example. Let's say that we're looking into drilling. So the data to the right are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to drill a distance of 5 feet in rock increases with depth at which the drilling begins. So depth at which drilling begins is the explanatory variable, and time in minutes to drill 5 feet is the response variable, right? So this is indicating that when they begin their drilling, when drilling began at a depth of 35 feet, it took them 5 minutes and 5.88 minutes. So this is not seconds. This is 5.88 minutes to drill 5 feet. Okay, so almost 6 minutes to drill 5 feet. When they started drilling at a depth of 50 feet, now it took them 5.99 minutes, right? So in general, the deeper you go into the earth, the harder the rocks are, the more difficult it is to drill. So in general, we see a pattern that the bigger this goes, the deeper you go, the longer it takes to drill 5 feet, right? This is sort of the guideline, but that's not always true. Look, at 75 feet deep, it took them 6.74 minutes. And then down at 95 feet, 20 feet deeper, it took them a little less, 6.1 minutes. So it doesn't always strictly go up as the depth goes down, but there's a general pattern that's true. Okay, so we refer to this as the explanatory variable, how deep you are when you start drilling. And we refer to the time it takes to drill 5 minutes as the response variable. So if we do a graph with these guys, so we create ordered pairs. So for example, we do ordered pairs, 35 comma 35 comma 5.88, and then this one we would do 50 comma 5.99, and so on and so forth, all the way out to 190 comma 7.9. Okay, so we have all these ordered pairs, and then we graph them all in the following way, create a scattergram. Scattergram looks like this. Okay, so we have time over here. That's the response variable. And then we have the depth at which we started to drill to drill. So if we look at the scale, it starts off with 0, 50, 100, 150, 200 over there. Okay, so for example, the 190 comma 7.9, that's probably roughly this point right here. This point right there, that little dot, is the ordered pair 190 comma 7.9. Good. And the one right above it, the 185 comma 6.89, that's probably this one. 185 comma 6.89. Right? Okay, so every one of these little dots represents an ordered pair from our table, where the input is the explanatory variable and the output is the response variable. Okay, so we're going to create a scattergram such as this one. In some cases, when it's a small amount of data, such as this one's relatively small, you might be asked to do it by hand. But if it's a more difficult one, if it's really big, then we might use technology for that, or it might be just presented to you. Okay, so let's cover how to get this with our calculator if we wanted to recreate this on our calculator. So let's go over to our calculator. Okay, so turn it on, hit clear, hit second, quit, get out of whatever screen you're on, then go to Stat, Edit, and then we're going to work with, say, the first two, list 1 and list 2. So hit clear, enter. Make sure that you're up there where the L1 is dark. Go up to L2, make sure the L2 is highlighted, and then hit clear and enter. All right, so list 1 and list 2. Going back over here, I'm going to refer to this guy as my list 1 and this one as my list 2. So I'm going to input these values into my calculator on list 1 and input these values into my calculator on list 2. This way. Okay, now that we inputted all our values into list 1 and list 2, let's come back over here. We're going to go, first of all, go right here where it says equal, y equals. Make sure that there's no equations on there, right? And also come down here and make sure there's nothing hidden down there. If there is something in there, hit clear. So if you see an equation like 2x plus 3 in there, then that's going to affect what we're trying to do. So either hit clear and get rid of it, or if you see it, 2x plus 6, and you want to save it, well then, see how the equal sign is dark? Use your arrows to get over to where the equal sign is, hit enter, and then it'll turn from a dark equal sign to a light equal sign. That means it's been deactivated, and it won't affect what we want to do. Okay? Also, there's a shortcut here where we see plot 1, plot 2, and plot 3. The fact that plot 1 is dark means that that one is on and active, and the other two are deactivated. Okay, so keep that in mind. Now we want to go over, it says stat plot. So we want to hit second, stat plot. That takes you to this menu. Again, from this menu, we can kind of see an overview of what's happening. Plot 1 is on. It's got a box plot. It's using data from list 2. Okay, plot 2 is off, plot 3 is off. Okay, so let's just go right into plot 1. Okay, so we want it on, that's good. Next, right now it has the box plot selected, but we actually want the first one now to create a scattergram. This very first one with little dots on there. Hit enter. Okay, next we want to tell it where our lists are. So our explanatory variable goes first, and that one we put on list 1. And then our response variable is the vertical axis, and that we put on list 2. Okay, so this was how deep you are when you begin drilling, and then this is how long it takes to drill 5 feet. Okay, all right, so now we have that. We got a choice of whether we want to graph little squares, little plus signs, or little dots. Little plus signs work for me. And if you have one of the color screen ones, then it'll ask you for colors. Okay, when we're done with all that, we're going to go over where it says zoom, and then down to the 9th option, stat plot. Enter. And there it is. Here is the calculator's version of that scattergram that we saw over here. This guy. side. Good. So this is roughly that. Notice, however, that the axes, the vertical axes and the horizontal axes are not really displayed. The computer or the calculator automatically kind of focuses in a good window that would capture the data for you. So if you want to make sure to include where the vertical axes and the horizontal axes are, you're going to have to go over where it says window. And now we want to change our x minimum and x maximum. So the fact that it says 19.5 and 205 in the x min and x max means that 19.5 is this value right here. It's not 0. Okay, and then like 205 is over there. So if we wanted to include the 0, we want to put x minimum at either 0 or even better, a little bit below that so that we can see that vertical line. So let's go to window, and then instead of negative 19.5, why don't we make it negative 10. Enter, and then graph. And now we go. Now we see the vertical axes. This guy right here is negative 10, and because it stretches past that, now we get to see that vertical axis. Before, it was right here, so it was hard to see where that axis was. Same with this. This is not the horizontal axis. This is not the x-axis yet, not necessarily. So let's go over to our window, and we see the y minimum at 5 and the y maximum at 8. So let's go back over here and change that y minimum. Right now, the fact that this is a 5.5 and this is 8.3 means that this is at 5.5 and that this up here is 8.8. Okay, so let's pick a better window. Now here I picked negative 10, but that's because in relation to how big this number is, negative 10 is not so big. But if I come over here and I make this negative 10, look what happens. Negative 10, if I go like that, it stretches this all the way down to negative 10, but this only went up to a height of 8.8. So we end up going way below the x-axis, and so it just creates a huge gap down here that is not including our data, so it's kind of dead space. Okay, so you want to pick a small negative number that's maybe about 5% as big, 10%, 5 to 10% as big as the maximum value. So you can get a very small, narrow little window there. So this, 10% of 205 is about 20, so 5% is about 10. 10% of 8 is going to be 0.8. Okay, so let's just make it, let's just try negative 1 and see what that looks like. And it's just a guessing and checking situation. No perfect answer. See how now we have like a small little gap. So it's a little easier to see the vertical axes and the horizontal axes, and we see where that scattergram is. Okay. So again, when we originally did it, the calculator just chose a little window right here so that we can focus on these numbers. And it sometimes gives you a misguided idea of what's happening. So be careful that the window influences your general perspective on what the picture looks like. But if we just want to go back to the way the calculator chose it, we can go back to zoom and then the 9th option. And again, it gives it to you. Okay, and this looks a lot like this one. Remember, every little dot on here, every little plus sign is an ordered pair from our table. If we wanted to be able to tell which is which from our calculator, we can hit this button that says trace, and then there'll be a little blinking guy, and up here it tells you the ordered pair, L1, L2, that it's plotting those values. And so here, this little blinking guy is 35, 5.88. That corresponds to this table value, the first table value. Good. And then if we go to the next one, it's 50, 5.99, and then the one after that is 75, 6.74, and then 95, 6.1, and so on and so forth. So we can dig around and find the one we want. Okay, so we know how to create a scattergram, both by hand as well as with our calculator, but what does that mean? Right, so let's explore why we care about that and what we're going to do with it in our work. These are the types of things we're looking for when we're working with scattergrams. We're trying to see if all those dots tend to follow some sort of linear path. In this class, we really only care about linear paths. So, for example, after I create my scattergram, it might look like this, which would indicate that there's a pretty strong direction this way, right? They kind of follow this path. Good. And then there's, or my scattergram could look like this. And this is indicating that the strong linear as well, right? Now this has a negative slope, whereas this has a positive slope, right? So a positive linear relationship, a negative linear relationship. Or it could be that my scattergram has this kind of a relationship, like some sort of parabola, for example. Or it might have something like this, which seems to be some sort of a cubic kind of relationship. Or some other complicated thing. Maybe it makes a happy face for all we know. But it might not have anything at all, like just random chaos like this one. In this class, all we care about is linear relationships. Yes, it's a linear relationship. No, it's not a linear relationship. If it's one of these guys down here, whether it's some sort of relationship that's complicated or whether it's just random chaos, either way, all of these down here for us are just simply classified as not linear, non-linear. Okay, so we just care about linear relationships. And then, well, to further classify it, we care about whether it's got a positive response, a positive linear response, or a negative linear relationship. Okay, so two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of another variable, and below average values of one variable are associated with below average values of the other variable, right? So that's what this is right here. Kind of focus on this. As we take our explanatory variable, as we get kind of rather large ones over here, the larger values, they're kind of associated with sort of the larger response variables. And when we go in this direction, so as we go this way, we end up getting the larger values in the response. On the other hand, as we get smaller values of the explanatory variable, as we go that way, we end up getting smaller values of the response variable. Right? Larger means the outputs are larger, and then the smaller the explanatory variables, the smaller the response variables. This describes a positive linear relationship. Right? That's what this is attempting to describe down here. On the other hand, we're going to have two variables that are linearly related are negatively associated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated whenever the value of one variable increases, the value of the other variable decreases. So negatively associated. So again, for example, this one, now we have the opposite case, that as we input larger and larger and larger values of the explanatory variable, the response variable is getting lower. Good. On the other hand, if we input smaller and smaller values as we go this way, smaller and smaller, the outputs get larger and larger and larger. Good. So when the relationship between these two variables is described this way through a scattergram, we say that they have a negative linear association. Okay, but we need more than that. That's good to just kind of ballpark it and get a sense of whether there's a positive or a negative linear relationship. But we need more than that. But you know what? Actually, first, let's look at some examples. So let's just generate some scattergrams and just judge whether we think that there is a positive or a negative association or neither nonlinear. So this is just going to generate random samples. So here's a random scattergram, right? So we might look at that and decide this just looks like random chaos, right? Maybe. So sometimes it's really hard to determine that by just looking at it. And sometimes it's a little easier. Like, yeah, it seems to be kind of going that way, right? If a new variable is a new value, a new data point is gathered, I would guess that if that point is this way, the x coordinate is over here, it would probably have an output value that's associated way over here, right? Larger values are connected with larger values and smaller values are connected with smaller values. I would guess that this has a positive relationship. Positive still, but a little weaker, right? I was a little more confident before, but this is still fairly strong evidence that there's a positive relationship. We're back to, I think, chaos. This is just sort of random chaos. I'm not really sure if it's positive or negatively connected. Here's one where it seems to be negatively connected, right? It seems to kind of be going this way. So when we input, when the explanatory variable is kind of small, the response variables are kind of big. And then the other way around, when the x coordinate values are kind of large, then these kind of get smaller, right? So if I told you a new data point is 22, guess where it would be? It would be a bad guess that it would be down here. It's possible, but it seems unlikely, right? It seems more likely that it would be somewhere up here. Okay, all right, let's try a new one. Okay, another one that I think is more positive maybe, but I'm a little less confident. I'm a few dots away from this just looking like chaos, but it tends to go that way, right? This tends to come down this way. This tends to be a negative linear correlation. Negative, but very unconfident, right? Because, I mean, I'm a few points away from it being chaos. If there was just a few dots over here, I'd be convinced that this was chaos. But somehow my eyes see this to come a little bit this way and have a negative relationship. Oh, this is a very strong positive one, right? Seems pretty obvious that they just go that way. Good. Okay. Oh, even stronger. Very, very confident that they go that way. If a new data point came in and I told you the input value is 80, what's the output? My money would be that 80 would be associated with something over here, right? It wouldn't be down here. I wouldn't put a lot of money that 80 is connected to a value of 5. Good. On the other hand, if you gave me the input variable is 20, I would guess, yeah, it's probably around here somewhere. I wouldn't guess 100. It seems unlikely, right? This is establishing a pattern, a pretty strong pattern. Okay, so we can play this game all day, just randomly assigning scattergrams and then visually deciding if there is a strong positive relationship, a strong negative linear relationship, a very, very strong positive linear relationship, or just random chaos, right? So we can just kind of do that by looking at it, but we need something more, something mathematical, something that we can calculate and tabulate and compare, and that's what we're about to get. So the linear correlation coefficient, or the Pearson product moment correlation coefficient, is a measure of the strength and direction of the linear relationship between two quantitative variables. The Greek letter rho, this guy right here, rho, represents the population correlation coefficient, and then the letter R represents the sample correlation coefficient. We present only the formula for the sample correlation coefficient. So for us in this class, at least right now, we are only going to be focusing on R, which represents the sample correlation coefficient. We don't really work with calculating the calculation for the population correlation coefficient at this point, right? So for us, we're really only focusing on R, the value of R. So R is going to be an equation. We'll get to it right now. Whose result, once you calculate the whole thing, and it's pretty ugly. Let me brace you. But once you calculate the whole thing, it'll be an answer that helps us numerically establish the strength of and the direction of a linear relationship between two variables. Okay, so here's the equation. R is equal to the sum of the product of these two things. So x sub I minus x bar over s sub x times y sub I minus y bar over s sub x. And the whole thing gets divided by n minus 1. So we can take a look at this little ledger down here to get a sense of what all these variables represent. So x bar is the sample mean of the explanatory variables. S sub x is the sample standard deviation of the explanatory variables. Y bar is the sample mean of the response variables, and S sub y is the sample standard deviation of the response variables. N is the number of individuals in the sample. Okay, so this might look familiar from when we worked on our z-scores, right? Each individual x coordinate minus its mean divided by its standard deviation. This is finding the z-score of each x, right? So another way to describe this R is that it's equal to z-score z-score of x sub I times the z-score of y sub I, and then we add those together, and then the whole thing gets divided by n minus 1. Good. Kind of maybe. So let's further explain what this is. Let's say we had a little table that had x's and y's, where this is the response variable, and this is the explanatory. So then this would be 1, 2, 3, ... down to n, right? So there's spot number 1, let's call that x1, x2, x3, ... all the way out to x sub n. And then this would be y1, y2, y3, ... Okay, so we're going to find the mean of all the x's, that's x bar. We're going to find the standard deviation of all the x's, that's going to be s sub x. And then for the y's, okay, that goes out to y sub n. We're going to find the mean of all the y's, that's y bar. And then we're going to find the standard deviation, the sample standard deviation of all the y's, that's s sub y. So now if we take the individual point, right, x1 minus x bar all over s sub x, that's the z-score associated with x sub 1. Good. So we find that z-score, and then we multiply it by the z-score associated with y sub 1 on that list. So it's y sub 1 minus y bar all over s sub y. So we do that for this first ordered pair. And then we do that for the next ordered pair. Plus, now x sub 2 minus x bar over s sub x times y sub 2 minus y bar over s sub y, right? And then we do it again. So we keep doing this over and over and over, and we do it all the way down to the last one. So we keep going, and we don't stop until we get to dot, 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 plus, and then the very last one is x sub n minus x bar all over s sub x, and then y sub n minus y bar all over s sub y, right? So that's the last one. And then we take the whole thing and we divide it by n minus 1. And that is the value of r. Okay, so again, these guys can be thought of as the z-score. Z-score of x sub 1, and this is the z-score of y sub 1. And this is the z-score of x sub 2. And then there's the z-score of y sub 2. And so on and so forth. So there's the z-score of x sub n. And this is the z-score of y sub n. Okay, so that's what this is describing. In this class, we are not going to be focusing on how they got that. That is really complicated, but trust me, there is valid mathematical justifications for these equations. They're just really, really ugly and far and away beyond the scope of this class. It's one of the reasons why I'm not a huge fan of teaching this class. It's because there's so many formulas that we present without really justifying it, and I think that that's not a great way to teach math. It just makes math, you know, really mysterious, and I'm not a fan of that. So if I had it my way, we would spend some time thinking about where this came from and why. But the powers that be say that that's not really in the scope of this class, so we're not going to do that. You're not responsible for that. So for us, we just have to know this formula. You don't even have to memorize it. You just have to know when it's time to use it, and then you have to know, calculate it, know how to use it. Okay? All right, so we'll cover how to figure this out, how to, practically apply this whole thing. As you can see, there's a lot of calculations. We're going to use our calculator to assist us with the arithmetic of it all, and organize our values in tables, so we can do column operations with our calculators and sort of help us get to the answer. Okay, but let's skip that for a minute and just think about, what is this r value? Okay, once you calculate this whole thing, the value r will always be a number that is between -1 and +1 inclusive, right? It could never be anything else. If you get an r value, that's different from that, you did something wrong. So here on the number line, here we have +1, and then over here we have -1. R is going to be a number somewhere in there. After your whole calculation of z-score 1, z-score 2, like the whole thing, you're going to get something in here. If you did all that work and you end up with r equals to 1.2, you did something wrong. Okay? It's never going to be bigger than 1. It could be 1, and it could be -1. It could be 0. Otherwise, it's going to be some decimal right in here. Okay? So from -1 to +1, these are valid values of r, the correlation coefficient. Okay? So the linear correlation coefficient is always between -1 and 1, inclusive, so we include the endpoints. Okay, and then what does that mean? If r equals to +1, if you get that whole equation and you end up getting that r is exactly right there, it's exactly equal to +1, it means that there is a perfect positive linear relationship between the two variables. It means that if we created a scattergram, that the scattergram would look like this, a perfect linear relationship that has a positive slope, kind of like that one. It could be that one, or it could be this one. So R doesn't give you any sense of how steep the line is. It just tells you it's linear and it's positive, but it doesn't tell you how steep it is. So it could be maybe this one, right? Okay. So if R is exactly 1, it's a perfect positive linear relationship. On the other hand, if R is -1, exactly equal to -1, so you get an R value that's exactly -1, then the relationship has got a negative linear relationship. So maybe the little dots might look like this, a perfect straight line, and it's got a negative slope. Again, it doesn't say anything about the steepness of it though. So it could be that maybe it just has a very subtle negative relationship like this. But it's a it's a perfect straight line. It just has a negative slope. Okay, so that's what it means when you have a -1 or a +1 as the result of your equation. Okay, but now what if we're not exactly +1, but we're getting close? It's a large positive decimal. Okay, so as we get closer and closer and closer, as the R value gets closer and closer and closer to +1, the closer we get to +1, the stronger the statistical evidence that we have a positive linear relationship. And then on the other hand, when we get a decimal value that is negative, a negative decimal value that's close to -1, well, again, the closer and closer we get to -1, the stronger the statistical evidence that we have a negative linear relationship between our variables. Okay. Well, how close is close enough? At what point do I go, yep, we have enough evidence? Well, we have a table for that, so we'll cover that right down here. Well, what about when it's 0? If R is close to 0, then little or no evidence exists that there is a linear relationship. So R close to 0 does not imply no relation. It does not imply no relation. It just implies no linear relation. Okay, remember that up here we established that it might have some sort of relationship like this one, but this R value can only detect whether it's linear or not linear. That's all. Well, and also whether it's positive or negatively associated. But if the relationship is parabolic, for instance, our R value is going to be close to 0. Okay, so it's just indicating that close to 0 means that we do not have strong evidence that there is a linear relationship. Okay, the linear correlation coefficient is a unitless measure, so it doesn't have any units, and it's just being used for this specific purpose to establish how strong the relationship is between two variables in terms of a linear relationship. And the correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. And we'll see that in a little bit as well. Let's, before we dive into the nightmare of figuring out the how to calculate it, let's go back to our scattergram generator here and guess the value of R. Okay, so let's come up with one. Okay, so here it looks like it's going to be negative, right? So how strong? If they were in a perfect straight line, it would be a -1. But this isn't quite a perfect straight line, but it is a very, very strong relation here. So I'm going to guess -0.95 for this one. Let's see how close I got. The real one would have been negative 0.807. Okay, so I was a little off. Okay, so this has an R value of negative 0.807. The result of that really ugly calculation would have been this. All right, let's try a new one. Okay, now I'm learning my lesson. This one is a little less strong than the other one, I think, but it's still negative. So I'm going to guess that this is negative 0.7. Yep, okay, I'm getting closer. The R value result for this one is negative 0.73. Okay, try a new one. How about this one? Now it looks like it's a positive relationship. So I'm going to guess that this has a positive 0.8. Ooh, okay, so this one's positive 5.8. So I was guessing that it was stronger than it actually was. Okay, let's try a new one. This looks like almost randomness to me. If I had to guess, there seems to be a few more this way. I'm gonna guess negative 0.2. Even more closer to 0 than I had guessed. So it's really close to total randomness here. So there is no linear relationship here. Okay, a pretty weak negative one, I would guess. So I'm going to guess negative 0.4. Was right on the money. Really, really close. If you guys want to play, here's the address. Or you can type in Rossmann-Chance applets. Rossmann-Chance applet collection. And then it's this one. Guess the correlation. Right? So Rossmann and Chance have this fantastic website that has all sorts of little applets for statistics. So I'll be referencing a lot of these in the coming sections. Well, you're welcome to go right over here and play with this on your own. It's a lot of fun. It's great at parties. So you can also change the number of points. So here I just randomly picked 100. But we can make it bigger. How about 500 points? So see, we have a lot more points. Okay, and that seems to be a very strong relationship this way, right? So negative, I don't know, let's make it negative 0.8. Negative 0.82. See, I'm getting better at this. Oh, that's a very strong positive linear relationship, right? I'm going to guess that this has an R value of 0.92. Ooh, 0.909. I'm getting really good at this game. Ooh, that looks like chaos. That looks like random chaos. It's not linear. It's not anything. I'm just going to guess 0. 0.008. Okay, so I think you get the point now. All right, back to this guy. Okay, so now we got to actually calculate it. We know how to interpret it. We know what it's supposed to mean, what it's doing. Okay, so here's some other examples to look at. So a perfect, right there in a perfect straight line, this scattergram would generate a positive 1 for R. Here, okay, it's pretty close to positive, very, very strong. This generates a 0.9. Okay, still positive, but it's a little bit more chaotic. If we had like just a few more points, like 3 or 4 more points, right? If this had like a couple more points here, you'd be convinced this was just random chaos. But okay, it's kind of close. So this generates a 0.4. Here we have a case where we have a perfect straight line and it's got a negative slope, so this generates an R value of negative 1. Here it's still negative, but it's a little bit more chaotic, a little bit more, but there's still very strong evidence that it's got a negative linear relationship. So R is negative 0.9. Good. A little bit more chaotic. We're just a few more points from being convinced that this is random chaos, right? So this generates a negative 0.4. And here we do just have something really close to 0. It just looks like random chaos. There is no positive or negative linear relationship of any kind. And then we have something that definitely has a relationship. This definitely looks like a parabolic relationship of some kind. But this R value only detects linear. yes linear, no linear, and then whether it's a positive or negative linear relationship. So here the R value calculated would again be really close to 0. Okay, so now let's get on to actually calculating the R value. Okay, so back to this information. To determine the R value associated with our drilling, right? At 35 feet, it took us 5.88 minutes to drill another 5 feet. At a depth of 50 feet, it took us another 5.99 minutes to drill another 5 feet, and so on and so forth. So here is how we can calculate the correlation. I would strongly recommend that we create a table like this, that you do this on your own work when you want to find the R value by hand, if you're asked to do this on your homework. So on our table, we list our X coordinates and our Y coordinates, and then the first thing we have to do is focus down here and figure out the mean and standard deviation of the x's. So find the mean and standard deviation of these values. Then find the mean and standard deviation of these values. Okay, so let's do that with our calculator. I've already inputted all of these things into list 1 and list 2 from earlier when I did my scattergram. So go to list 1, put these guys. Go to list 2, put these guys. And now I want to find the sample mean and the sample standard deviation of the x's, and the sample mean and the sample standard deviation of the y's. So let's do a one variable stat on each of these lists in order to get those results. Okay, so here was my scattergram, stat, edit, enter, and then confirming that list 1 had all of those values. Okay, list 2 had all those values, okay. So go to stat, calculate one variable statistic on list 1, enter, make sure that frequent list is blank, calculate, and then here's the mean, x bar, that's going to be 126.25, and then the sample standard deviation, which is going to be 52.22874. Okay, so we got those two. Next, we're going to do stat, calculate one variable statistic on list 2. List 2. Good. And then we're going to go down, calculate. And we got the sample mean, 6.9858. Here it is. That's this one. And then we got the sample standard deviation, S sub x, which is 0.780774. That's this guy right here. Okay, once we have those four values, we're going to come over to our list again. So hit stat, under edit, hit enter, and we're going to use some of these other values. So I'm going to clear my list 3, clear, enter. List 4, I'm going to clear that guy, clear, enter. And finally list 5, clear, enter. So I'm starting with a clean slate here of all my lists. Okay, so for list 1, let's recreate for list 3, let's recreate this. Let's make this our list 3. List 3. How do we get list 3? Well, it's each value in list 1 gets subtracted by the mean and then divided by the standard deviation, right? So for this very first value here, this for this very first value there, it is the result of having 35 minus 126.25 and dividing it by 52.22874, right? This is equal to the negative 1.74712, right? So all of that goes right there. And then for the next one, all that changes. In fact, let me put it in color. Okay, so for this first one, it was 35, and that's how we got that. For the next one, The next one is just going to be 50. Input a 50 right in there. And then the one after that, well, that's just going to be 75. Good? Okay, so what we need is to put all the values of list 1 into here. And that's how we're going to do column operations. We're going to state that list 3 is going to be equal to L1 minus the mean, which was 126.25 divided by the standard deviation, which was 52.22. 52.22, and then you can put the mode decimals in there to be more accurate. Let me zoom out a little bit more. .82874. Okay, so this is the equation we want right here so that our calculator can generate this whole column right here. Okay, so let's go to my calculator. I'm going to put that list 3. Make sure that you're highlighting the L3 in order to do column operations. That this one is going to be equal to, now I'm going to put it in parentheses to make sure that it doesn't do anything weird. And then I'm going to do L1 minus 126.25, close parentheses, divided by 52.22874. Enter. There. So now it generates this column right here. Okay. And notice that it doesn't quite give you as many decimals of accuracy in here, but they show more accuracy down here. So it's storing some extra decimals that you don't see. This looks like it just rounded to 2 decimal places, but it doesn't. As you use your arrows to highlight that little square, you'll see the more expanded value that's being stored for that result. So this one is that one. And then if you go one more, you get that one. And if you go one more, you get that one. Okay, so we have all of these values onto list 3. Now let's move on to list 4. So now I want this guy to be list 4. And I want list 4 to do the exact same thing, but I wanted to do it with these values in here. So the little equation I'm going to want is that list 4 is going to be equal to list number 2 minus its mean minus 6.985833 divided by its standard deviation, which is 0.780774, and that's the little equation that goes right in here, column operations, so we can generate this whole list right here. Okay, so let's go over to our calculator. And I'm going to do over to the right, make sure you highlight list sub 4, make sure everything below it is cleared, and you're going to type in L sub 2, oh, let's put parentheses, L2 minus its mean, 6.985833, divided by, close parentheses, divided by its standard deviation of 0.780774, close parentheses, enter. Whoa, made a mistake. Go to L2 minus 6.88. Oh, close, delete this guy. I opened parentheses there and I closed it there, and I didn't open parentheses again, so there was no need for me to close them, right? So I didn't need that extra parentheses at the end, that's all. Okay, hit enter, and there we go. This should generate all of the values here on this list. negative 1.46, yup, negative 1.2, yup, okay. So all of these values equal all of these values. Okay, so far so good. So these are the z-scores. These are each of the z-scores. This is the z-score associated between this one in its distribution. Right? This is the z-score associated to 50 within the distribution of x's. Good. This is the z-score of this y value amongst its distribution of y values, and so on and so forth. And so the next thing we need to do is to multiply those two values together. I need to multiply list, this is going to be my list 5 now, list 5. And my little equation is just going to be that list 5 is just going to be equal to list 3 times list 4. I just need to multiply those two numbers together across, and that'll be list 5. Okay, so list 5 is just going to be equal to list number 3 times list number 4, enter, and that is going to be this values. Right, so that's these guys right here. Okay, so the next thing, the last thing we need to do is to add them together. Notice that, so this guy right here, let's do the equation. Our equation for R is that R equals, and it's going to be x sub 1 minus x bar over s sub x multiplied by y sub 1 minus x bar over s sub y. Oops. Over minus y bar. Okay, and so this is for the first values. And then once we're done with that, we do it for the next one, plus, and then it's going to be x sub 2 minus x bar over s sub x times y sub 2 minus y bar over s sub y. And so this is for the second one, right? And we keep going all the way down until we get to the last one. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like there's 12 entries. So we would keep doing that, dot, 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 all the way out to the very last one, which in this case seems to be the 12th one. X sub 12 minus x bar over s sub x times y sub 12 minus y bar over s sub y, and this is the 12th one. And then once you add all of those up, then you divide the whole thing by n minus 1. Okay, well, in our table, this whole table over here, this number right here is this number, right? We found the z-score of the x sub 1, the z-score of the y sub 1. We multiplied them together, and that's what this number is. 2.474501. Good. And then the next one, this one, that's this number. That's 1.862051. And then the very last number, 1.42, that's this guy. 1.429. Good. Okay, so what do we have to do? We have to add all of these numbers. So we got to sum all of these. Luckily, they were already in my calculator, and there's an easy way to sum all of these things. We just have to do a one variable stat on list number 5, and that'll give us this little summation, which you can get very easily. Okay, so now go back and do stat, calculate one variable statistics on list number 5. Down, down, enter. And remember, we're looking for this guy, the sum of the entries. This gives you the mean of the values in list 5. That's not what we want here. This gives you the standard deviation of the values on list 5, which again, we don't want in this case. We want the sum of all those values, the sum of those entries, which is this number, 8.50103. Okay, so then that is this number right here. So the table already gives you that result. The sum of all of these guys is this. And once we have that, we're home free. All we have to do is divide by n minus 1. Okay, so once we get that value, we take this number, that's this one, right? That's the hard part. And then we divide by n minus 1, where n was 12 in this case because there are 12 entries. There is 1, 2, 3, 4, dot, 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 all the way down to 12. There are 12 entries, n equals to 12. And that's why we divide by 12 minus 1, which makes it 11. And then we divide it, and we get this right here. The R value associated with this distribution is a 0.773. Okay, well, it's positive, so that means that we're indicating that there's a positive linear relation. Okay, we're aware of that. And we know that the closer we get to 1, the stronger the evidence that there is a positive linear relationship. But is 0.77 good enough? Like, should I just conclude, in the yes or no, yes it's positive or no positive, can I conclude that there is enough statistical evidence? Where's the cutoff point, right? At what point do I decide if it's good enough? Well, that's what this table is about. The critical values for correlation coefficients. What we do is, the way we do this is we first of all have to pay attention to how big the value of n is. So for us, in this little example, it was 12, right? So we're going to look at this number, which means it gives you that number. What this is saying is it tells you the cutoff value for both the positive and the negative direction. So if we think of it on a number line, here is a number line for r, and we know that it only goes from -1 out to +1, and then there's like a 0 right in here, right? So the fact that this decimal is 0.576, that's a little bit more than halfway, right? Because halfway would be 0.5. So say something like right there. Here is 0.576. Okay, so even though it doesn't include the negatives, we have to know automatically that it also means that it would be the same over here, sort of its mirror image, but negative. Negative 0.576. Okay, so now if an R value lands over here in the green zone, that means that it's to the left of this number, but of course equal to or less than 1, -1, right? So if it lands in there, then we have a negative linear relationship. We have enough statistical evidence to conclude that there is a negative linear relationship. If, on the other hand, our R value lands somewhere in this little zone, it means that we do have sufficient statistical evidence to conclude that there is a positive linear relationship. Okay? Positive linear. And then over here we have negative linear. And if we get something in the middle, of course, then that must mean that there is no statistical evidence of linear. No evidence to support linear. right? I mean, there might be a linear relationship. We just don't have the evidence for it. Maybe go out and get more data points. We only got 12. If you go out and get another 30 points, maybe eventually it starts to look linear, right? So for example, maybe after initially getting some data points, it might kind of look like this, and you're like, I don't know, that looks like chaos. That's not linear, right? After 1, 2, 3, 4, 5, 6, if we calculate R for this, it's going to be really close to 0. It's not very strong. But if we keep going and get more data points, maybe after we get a bunch of data points, we go, wait a minute, you know what? Maybe there is a strong linear relationship. Good? Okay, so just because we fail to find statistical evidence, that doesn't mean that there is no linear relationship. It just means that we don't have the evidence for it. Also, remember that there might be a non-linear relationship. It might be that the dots, kind of form a pattern like this. Like, oh yeah, that's definitely a pattern right there. It's just not linear, right? This might be some sort of a cubic pattern of some kind, but it's just not linear. So it's going to give you an R value that's close to 0. Okay, so for our purposes, right, we just established up here that it was 0.773 and n equals to 12. So for us, we got 0.773. That's, get rid of this thing. .773, that's right over there, 0.773. So we do have sufficient statistical evidence to conclude that there's a positive linear relationship between the depth at which you start drilling and the length of time it takes to drill 5 additional feet. Okay, so determine whether a linear relationship exists between the time to drill 5 feet and the depth at which drilling begins. Comment on the type of relationship that appears to exist between the two. Okay, so we have our data. We calculated our R value at 0.773. For n equals to 12, the critical value is going to be 0.576. And because 0.576 is greater than 0.576, there is a positive linear relationship between the time to drill 5 feet and the depth at which drilling begins. Okay, so according to the data obtained from the Statistical Abstract of the United States, the correlation between the percentage of female populations with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Okay, so does this mean that a higher percentage of females with bachelor's degrees causes higher percentage of births to unmarried mothers? Okay, what is this saying out of nowhere? Okay, so this is describing that if we do a scattergram, correlation between female population with a percentage with a bachelor's degree. So we put bachelor's degrees over here. In this direction, percentage is percent of population. And then in this direction, we put percentage of births to unmarried mothers. So these are births to unmarried mothers. Those are bastards, right? So unmarried mothers, unmarried mothers, births, percent of births in this direction. Well, this is saying that there is a very strong positive linear relation, right? According to the data, there's a correlation between females and married, and it's 0.94. So we know that indicates a very strong positive linear relationship. So just to make something up to visually have something to go by, it might look something like this, right? Just dots that kind of go this way. This indicates a very strong positive linear relationship. Something like that. meaning that the higher this goes, right, the higher the percent of our population that has bachelors, the higher the percentage of unmarried the births to unmarried mothers. Good. Or the other way around, right? A low value over here, a low percentage of population that has a bachelor's, the lower the percentage of births to unmarried mothers. Okay, so we just have to accept that to be true based on data obtained. So it's not our job to question that. That's just the way it is. The real question is, how do we interpret that? And a terrible way to interpret this is to assume that because this is true, that if we manipulate one of these, it'll affect the other, right? Does this mean that a higher percentage of females with a bachelor's degree causes a higher percent of births to unmarried mothers, right? Does this mean that if we come in and change this, manipulate this, get more females to get a bachelor's degree, does that mean that this will automatically also be affected? Or the other way around? What if we reduce this? We stop women from getting a bachelor's degree. Is that going to automatically reduce the percentage of births that are born to unmarried mothers, right? So what we're driving at is that when we have a relationship such that manipulating one affects the other, we have a causational relationship. One causes the other. So we can manipulate one and it affects the other one. But we haven't established that. Just because we establish that there's a linear relationship does not mean that there is a causational relationship. There is just a correlation. A correlation just simply means that they're both behaving in the same way, but it doesn't mean that one causes the other. So it would be silly to try and manipulate the output by manipulating one of the variables. Right? This is a very, very common misconception in everyday life. People will try and trick you with that all the time. Just because two things are correlated does not mean that there is a causational relationship between the two. Does not mean that manipulating one will affect the other. Okay? So the correlation exists only because both percentages have been increasing since 1990. It is this relationship that causes the high correlation. In general, time series data collected over time, may have high correlations because each variable is moving in a specific direction over time, both going up or both going down over time, one increasing while the other decreasing over time. When data are observational, we cannot claim a causal relation exists between the two variables. We can only claim causality when the data are collected through a designed experiment, right? So lots of stuff moves in the same direction over time. We can look at home prices over time. Let's say we decide to do a graph, and we do home prices over here, home values. And then in this direction, we could do oil prices or gas, price of gallon of gas. Guess what? They've both been going up over time, right? They've kind of been dancing around, but they've both been going up. But that does not mean that one causes the other, right? This doesn't mean that if we say, oh, look, they're both correlated. Okay, we could say they're correlated, but you can't assume that because we bring down the price of gas, that that'll automatically bring down the price of homes, right? That would be silly. If somebody says, oh, home prices are too expensive, we can't afford it. Let's pass a new law that makes gas really cheap. Let's bring gas all the way down to $1 a gallon, and then let's watch those home prices go down. That's not going to happen, right? Just because they're related to each other, they're correlated with each other, doesn't mean that one causes the other. Lots of stuff has been going up, right? Ice cream sales, ice cream prices, ice cream sales in terms of volume. All those things have been going up over time as well. Ice cream prices have been going up, so have home values, and that can just be connected to inflation, right? A dollar doesn't buy you what it used to. So at one point, ice cream was only like a quarter. You can go down and get like an ice cream for a quarter. Can't get an ice cream for a quarter anymore. Really anywhere. So prices have been going up because of inflation. Okay, but let's just say volume of ice cream. How much volume is of ice cream is made and sold every day? That's been going up too, and so have home values. But that's probably more connected to the fact that also the population has been increasing. We sell a lot more ice cream today, volume-wise, as compared to say 1950, because there's just a lot more people here as compared to 1950. The population has doubled since then, maybe more. So just because there's a correlation doesn't mean that one causes the other, right? It would be silly for someone to say, I know, let's bring ice cream prices down. Let's just make ice cream back to only being a quarter to be able to get ice cream, and that should somehow affect our home values. That's not true, right? So there's all kinds of correlations that can be established, and there's a lot of funny ones out there. So I looked up some funny ones. So here's some funny correlations that exist. So U.S. spending on science, space, and technology, and suicides by hanging, strangulation, and suffocation. Okay, clearly one has nothing to do with the other, but there's a really strong correlation, right? They're both being measured over time, and that's why this graph looks a little bit different than our scattergram. But we can just pay attention to this right here, the R value. It's got a 0.99 correlation. They're very closely correlated. However, it would be silly for someone to think that we can affect one by manipulating the other. So like obviously we want to reduce suicides. Does that mean we should reduce spending on science? No, that's silly. They're correlated. That does not mean that the one causes the other. Good. Here's another silly one. Number of people who drown by falling into a pool, and films by Nicolas Cage. Okay, obviously silly to think that one causes the other, but they're correlated. There is a 0.66 correlation, positive linear correlation between the two. Here's another one. Per capita cheese consumption, how much cheese are we eating per person? And then the number of people who die by becoming entangled or tangled in their beds. That's a weird way to die. But look at their correlation, 0.94, right? So they're strongly correlated. When one goes up, the other goes up. When one goes down, the other one goes down. So they're strongly correlated with each other, but it's silly, dumb to think that one causes the other, right? So as we push to eat more cheese, if you see commercials that eat more cheese, it would be dumb for someone to come in and say, oh no, that's going to increase how many people die of getting tangled in their bed sheets, right? So just because two things are correlated doesn't mean that one causes the other. Here's another silly one. Divorce rates in Maine and per capita consumption of margarine. So divorce rates and margarine. Right? Completely silly to think that one causes the other, but they are strongly correlated. Look at this, 0.9925, a very, very strong positive linear correlation. So when per capita consumption of margarine increases, the divorce rates increase, right? Past margin means increase more divorces. So they're correlated. I'm not saying that this correlation is wrong. There's a lot of stuff that's correlated with each other. It's just that one doesn't cause the other, right? There's no causality. Last one, age of Miss America and murders by steam or hot vapors or hot objects. Another weird, creepy way to die. Okay, so the age of Miss America, strongly correlated. There's a 0.870127 correlation, positive linear correlation with murders by steam. But again, one cannot cause the other, right? Just because we come in and manipulate the age of the next Miss America pageant winner, right? It does not mean that it's going to have any actual impact on the number of murders by steam. Okay? All right. Correlation is not causation. Very important in statistics. If you walk away with anything, that should be one of the things. Correlation does not mean causation. It does not mean that one causes the other. What it could mean is that over time, a lot of stuff just happens to move in the same direction. Or it could mean that there's a lurking variable there, something that maybe we didn't think of that's actually affecting both things. For example, the we could have the price of the car, the family car. Let's put let's say price of car you drive. The price of the car you drive is also connected to life expectancy. Life expectancy. So if you drive super expensive hypercars, like way out here, like say a $5 million car, compared to like the cheapest car you can possibly drive, let's say that there is a $700 car. You can buy a used $700 car, right? And then of course there's everything in between. So maybe say somewhere around here is your standard family car that's maybe in the neighborhood of a $30,000 car. And then it goes up to this ridiculous $5 million car. Okay, well, shockingly enough, life expectancy goes up. The more expensive the car, the longer you're expected to live. Right? There is a very strong positive linear correlation between the price of the car you drive and your life expectancy. Right? And initially that seems counterintuitive because if you think of these hypercars, they're not really very safe, right? They go really fast. You get in a car accident, you get totaled, and it's not it's not super clear why driving a really expensive super hypercar is correlated with a long life expectancy, right? But if you think about it for a little bit, then a lurking variable becomes apparent. If you drive a very expensive hypercar, if you drive a $500,000 Lamborghini, it probably means you have a certain amount of money, right? And if you have a certain amount of money, you have good access to healthcare, good access to nutritional food. You probably have a nice house with like a nice home gym. If you wanted to, you can easily get a trainer to help you out. You probably, not always, but you probably don't have a job that kind of affects your life expectancy. Not always. Could be an athlete that does something dangerous, but it could be family money. Maybe you just grew up there and you don't really do anything. You just hang out and collect the money. It's the family thing. Check comes in the mail. Okay, well, if you think about it, that lurking variable, the family wealth, is really what's affecting both. The price of the car you drive is connected by your family wealth, but your life expectancy is also affected by the family wealth, right? So it's that lurking variable underneath there that might be impacting things. So it would be wrong to think that one affects the other, right? It would be wrong if Lamborghini decides to come out with a commercial that says people that drive Lamborghinis are expected to live longer. It would be disingenuous, right? It would be implying that you should buy that car in order to live longer. And that is implying causality, which is not true, right? There's a correlation, but there is not a causation. So we shouldn't say, oh, you know what? I want to live longer, so I better get a more expensive car. That doesn't make sense. Okay. Good. Okay. What's another good one? Could be. Well, no. Okay. Let's leave it there. So a lurking variable is related to both. Another way to that two variables can be related even though there's not another way that two variables another way that two variables can be related even though there is not a causal relation is through a lurking variable. A lurking variable is related to both the explanatory and response variable. For example, ice cream sales and crime rates have a very high correlation. Does this mean that the local government should shut down all ice cream shops? No, the lurking variable is temperature, right? When the temperature goes up, ice cream sales go up, but so does crime. When the temperature goes down, gets really cold, ice cream sales go down. Nobody wants ice cream when it's really cold, but so do crime rates. Crime rates tend to go down. Okay, so here's another example. Because colas tend to replace the healthier beverages, and colas contain caffeine and phosphoric acid, researchers Kathleen L. Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. Okay, so the number of colas per week, 0, 0, 1, 1, and then the bone mineral density of these women. So this woman drank about 2 colas per week, and this is her density. This woman drank about 7 colas per week, and then this was her bone density. Okay, is there a relation? So the figure on the next slide shows the scattergram of the data. Okay, here it is. Here's that scattergram of the data. And just by looking at it, there seems to be a negative linear relationship, right? So the more the colas we drink, the lower this bone mineral value is going to be, right? Less minerals in our bones as we drink more colas. That seems to be it. But how strong is it, right? We need more than just a guesstimate. By looking at it, we need an R value. Okay, so the correlation between the number of colas per week and the bone mineral density is R equals to negative 0.806, right? So that would be the result of using that crazy formula we just did a little while ago. So if you had to figure it by hand, you would use that formula. The critical value for correlation for n equals to 15 from our table is equal to 0.514. And so that means that we definitely do have sufficient statistical evidence to associate a negative correlation, a negative linear correlation between these two variables. Good? But we cannot conclude causality. We cannot conclude that one causes the other. We can just conclude that they're correlated to each other. Of course, there could be other lurking variables that maybe are driving both. In prospective cohort studies, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So the researchers cannot claim the increased cola consumption causes a decrease in bone mineral density. Some lurking variables in the study that could confound the results are body mass index, maybe their height, smoking, alcohol consumption, calcium intake, and then physical activity, right? So in other words, even though they're correlated, they're both moving in the same direction, it seems like more soda consumption per week is associated with a lower density. Of course, the soda company is going to deny that and go, no, it's not our soda, it's not our fault. Look, it could be one of these other things. Maybe it's the body mass index or their heights or their smoking or their physical activity. There could be other lurking variables. The only way to establish causality is to do an actual experiment, a designed experiment. So the authors were careful to say that the increased cola consumption is associated with lower bone mineral density because of potential lurking variables. They never stated that the increased cola consumption causes lower mineral density, right? I'm sure that if they throw in the word that the increased cola consumption causes lower bone mineral density, I'm sure Coca-Cola wouldn't hesitate to jump in and sue them, right? Okay. So the only way to actually establish causality is through a designed experiment. What would this experiment look like? Maybe we grab 1,000 people randomly selected from our population, and we force them to drink a certain amount of soda, lots of soda every day. We force them to drink 1 liter of soda every single day for 10 years. And then we take at the same time another random group of people, right? Another 1,000 people. And then we do the opposite. We deny them soda for 10 years. You can never have a single drop of soda. Everything else stays the same in your lives, right? So they are allowed to do whatever physical activities they want to do. They're allowed to eat whatever they want to eat, smoke or not smoke, drink alcohol, don't drink alcohol. So that both groups kind of approximately have all the same stuff going on. Some people in both groups will be heavy drinkers of alcohol. Some groups, some people in both groups will smoke alcohol. Some people in both groups will be very active, physically active and fit. Some will not. So we end up having two groups that are almost identical, and the only thing we can really point at that is very, very, very clearly different across the board is that one group drinks a lot of soda and the other group is never ever allowed to touch soda. Therefore, if we actually do detect a noticeable difference in the calcium density, then we can say, you know what, it had to be the soda. That's the thing that was different between the two groups. That's how we can establish causality. Anything short of that, is just not an experiment, and it's not going to be as strong as an experiment. Okay, so correlations are fun and interesting, and maybe they point in a direction we should be looking at to create an experiment, right? So a good study like this one that establishes a strong correlation would be a great place, a great indicator that maybe we should be looking at soda, cola consumption a little stronger. Maybe do some sort of a study if we can to try and get a real answer. Of course, money and moral dilemmas can get in the way, right? It's hard to randomly pick a group of people and force them to never drink soda, and it's hard to pick a group of people and force them to drink soda every time. We can dilute that a little bit and say, well, let's take volunteers. Who wants to be in the group that never drinks soda, and who wants to be in the group that always drinks soda? But then that takes away the randomness, right? So we've diluted the power of our results because people can always claim that the fact that they self-selected into those groups affected the results, the outcomes of our experiment. Okay? All right, so correlations. We can establish correlations. We can quantify that correlation by finding the R value. And correlations do not imply causality. Okay, that's a good place to stop.